Okay? One or more substances are changed into a new substance, right? Something is changed into something new. If we have a physical change or a physical kind of, not a reaction, a physical change, do we form any new substances? In a physical change? No, right? The composition of that substance stays the same. But in a chemical change or a chemical reaction, that means we have some sort of a change that takes place. We might have a compound that breaks down into simpler compounds. We might have two simple compounds that come together to build a more complex compound. Or we might have, two complex compounds that mix and form something new as well. Okay? So these are processes in which a substance is formed into something new. There's two parts of a chemical reaction, and we've talked about these two parts before. Can anyone think about what that might be? Two parts to a chemical reaction, kind of the before and the after. Anybody? What's it called? The what?
The last one is product.
Yeah, good. Product. So what do we start with? The reactants. Very good. The reactants in our products are the starting and the ending points. Okay, so reactants are the starting, right? What we start with. What is reacting to form this product? Right? And when we write a chemical equation, which do we think, would the reactants go on the left side or the right side? They go on the left side, right? They come first. So the reactants are what is reacting together to form the products, right? Product is the answer to a multiplication problem, right? That's the final product. Same thing works here. Okay, so products are what is made. What comes from the combination of those reactants. Sorry, do we have what we need here? Okay. What could be a good indicator to us to know that a chemical reaction has taken place? How would we know that there's been some chemical reaction that has happened? How would we know that? Yeah, what do you think?
Change in color.
Change in color, good. The chemical composition changes altogether, good. What are some other things that might tell us that a chemical reaction has taken place? Like solid to liquid or something like that. Okay, sometimes those are physical changes. Sometimes we can see a change in state when we have a chemical change as well, okay? If we see something heat up, that's usually a pretty good indication that a chemical reaction is taking place, right? If there's some sort of heat that's being let off or energy that's being let off, right, light that's being emitted from that chemical reaction, there has to be some chemical equation or chemical reaction taking place, right? When you take a glow stick and you snap that glow stick, what do you think that does? Do you think the snap itself is what makes the light form?
The chemical in the glass.
Right, there's some chemical in there that is being released when you snap that glow stick to now form a chemical reaction with the other substance within that stick. Does that make sense? Right, so when you do that snap, it's not just a magic snap that makes this thing light up, right? It releases some chemical, and then this chemical reaction will take place to emit that light. Okay? Same things that goes with hot hands, right? If you break the inner shell of a hot hand, that thing starts to warm up. It's not magic, right? It's a chemical reaction that's taking place. Maybe it's magic. Okay. Some reactions you'll see basically have a combination of these kind of characteristics. Some will release both heat and light, both of which are good indicators that some sort of reaction has taken place. Okay, if our reaction starts to emit a gas or produce a gas, you'll see that maybe steam is not really the gas that we're thinking of here, because steam is a good indicator of heat, but it could produce O2 gas, hydrogen gas, all kinds of different types of gas that would tell us that a chemical reaction has taken place. Okay. Gases usually start out in bubble form, right? If we're in a liquid and we start to see these bubbles forming, that's a good indication to us that we have a new product being formed. This is not talking just about boiling, right? If I am boiling something, we see little gas bubbles start to form as well. This is a little bit of a different idea. Okay, so we know that it takes place if we see energy or heat. We know it takes place if we see a gas forming. Another way that we can tell if it's making a chemical reaction is if we have a precipitate. Any guess about what a precipitate might be? Yeah, Jenna, what do you think?
Something that is formed.
Yeah, pretty close. What state would you guess that it's in? Solid, liquid, or gas? Solid. These are solid. A precipitate is a liquid. Okay, that's all right. So if a solid appears when two or more liquids are mixed, that means a chemical reaction has taken place. So we don't usually see a precipitate when we mix water and milk, right? Hopefully no chunky things fall out of the milk. That's not a good sign, okay? But if we mix two things and a precipitate or a solid starts to fall out, you'll see that kind of sink to the bottom. That's a really good indication that a chemical reaction is taking place. Color change, we talked about that. So when we mix things and we get a new color, that means that a chemical reaction has taken place. And I'm going to teach you how to identify, based on our reactants, what do we think that might form, right? We're going to be able to identify or to predict the products that are going to be formed if these two things are going to mix. So when we write out a chemical reaction, it has to have everything that we know about that substance. Have to contain correct formulas. So you need to maybe start recalling those polyatomic ions that we learned and recalling our rules for naming. Okay, because if I say I'm looking at a reaction between potassium phosphate and sodium nitrate and you don't know what those compounds are, you're not going to be able to balance your chemical equation, which means you're not going to be able to predict your products, which could lead to a whole string of other problems. Okay, so I know you thought you were done with naming, but ta-da, you're not. Okay, sorry. Okay, correct formulas for products and reactants. Okay, we just talked about naming here. Okay. The law of conservation of mass has to be satisfied. So what does it mean when we talk about the law of conservation of mass? Yeah, Rachel, what do you think?
Matter can neither be created nor destroyed.
That's right. It cannot be created or destroyed. So what does that mean in terms of our chemical reaction about before and after? That's exactly right. Okay, the law of conservation of mass has to be satisfied. So that means whatever mass we start with has to be the mass that we end with. Okay, and we're not going to talk about mass of our chemical reactions just yet in this chapter, and we'll get to that in chapter 9. But right now we need to understand that especially the atoms that we start with, right? If we start with 4 hydrogen atoms on this side, our products have to have 4 hydrogen atoms somewhere. Okay, so that's going to be that balancing act that we go through in this chapter. Okay, same number of atoms of each element must appear on each side of a correct chemical equation. So that's kind of what I just said. If we start with 10 oxygen atoms as one of our reactants, that means on my product side, I'm going to have 10 oxygen. They don't have to be all together. They don't have to be in the same exact compound. But they need to be somewhere in my reactants. I can't let oxygens disappear randomly. $263. Okay, up at the top, these are our list of diatomics here. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Okay? So if you look at your periodic table, or look at this periodic table up here, excluding hydrogen, it makes a pretty even little 7 right here. Okay, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. These are the diatomics, okay, plus hydrogen. So these elements cannot exist on their own. So if I say I have a reaction of fluorine and whatever else, I can't just say single fluorine, right? It would have to be F2. Okay, the same thing, if I had hydrogen gas reacting with oxygen gas, it's not just H plus O, it's H2 plus O2. So those are those things you have to think about. When they are looking at single elements, it's not just them by themselves, it's a pair of them. Okay, so H2, O2, N2, so on and so on. Okay, so that's going to be something that you really have to kind of remember when you're writing chemical reactions. Okay, so if I say hydrogen gas, I'm not talking about H, I'm talking about H2. If I talk about oxygen gas, same thing, I'm talking about O2. Okay, so I'm going to give you some symbols that we might use in equations or that you might see in some equations. If I have a reaction NaCl plus H2O yields whatever, and you see a little S right here, that means that this salt is in solid form. Okay, so we're talking about it in solid form. That just means it's a little S in parentheses. You might see that. Okay, same thing goes with liquid. We would see an L in parentheses, and a gas you would see a G in parentheses. Okay, it's nothing new here. Jet, you all right?
Yeah.
Okay. And then our last one you might be a little bit more unfamiliar with. Okay, and it's an AQ. Okay, so if you see this AQ symbol, that means it's aqueous. Okay, and from our little bullet underneath here, but from the root of this word, what would you assume it probably means? Water, right? Okay, and luckily it tells you right here, in water. So when we see something that is aqueous, that means it has been dissolved in water already. Okay, so it is completely dissolved in water, so it's a solution at that point. Okay, those are pretty simple. We're not going to deal much with what it means to have a gas and a liquid react together and stuff like that, but you just need to understand that's what state it's in. That's how it shows you that. Okay, a single arrow listed right here. Okay, single arrow. This means yields. Okay, so the arrow tells us that we've made a switch now from reactants to products. Other compound, that means that's what it's going to make. Okay, so when you see a single arrow, that's what we're going to deal with in Chapter 8 and in Chapter 9, is a single-headed arrow. That's going to tell us this is what it equals. Okay, a double-headed arrow means it's what we call a reversible reaction. So that means it's going to go from reactants to products, and then it's going to go back, and then it's going to go back again. So that's when it reaches something called equilibrium. It's going to be able to keep going back and forth there. That's not something that we're really going to have to worry about yet. Not quite, because that's just a change of state. So evaporation is still water, going from liquid to gas. Yeah. Okay. So here's an example of just what a chemical reaction would look like. You don't have to write this down. We're just going to kind of look at what this means in general. Okay. So this equation is between potassium chlorate. Okay, do we see that's the name of that molecule? Yeah, potassium chlorate. This symbol tells us what? That this is a solid. Good, this is a solid. Okay, and what do you think this 2 in front of us, this coefficient 2 tells us? There's 2 of those atoms, right? And we can think of it on a molecular level and think of it as 2 single molecules of that, or we can think of it on a molar level, which gives us a much bigger quantity, and this could tell us there's 2 moles of that whole substance. It's the same ratio. Okay, so it doesn't really matter which way we think about it, but usually this coefficient is going to tell us there's 2 moles of it. We could also think of it as 2 single molecules. Okay, you can scale it way up or scale it way down, either one. This arrow tells us that this is the only reactant we have. Right? So what's happening for it to be able to form 2 different products? That's right. The bonds are breaking. It's breaking down. Right? So it forms potassium chloride and oxygen gas. Okay? We see this is still a solid. This is still a gas right here. So how many moles of potassium chloride formed here? 2. And how many moles of oxygen are formed? 3. Okay, so even though we only started with 2 moles of our substance, we see we formed 5 moles of 2 different substances. The conservation of mass is what matters, right? Those things weigh different things. So it's not like we have to have a conservation of moles, right? That's different than mass. Okay, any other questions about what this looks like? We're going to learn how to balance each sides of those and how we got how did those coefficients come to be, right? How did we know it was 2 and 2 and 3? Okay, so coefficients we just talked about here. We may need to represent more than one molecule of a compound to make sure we satisfy that conservation of mass. We have the right number of oxygens on each side, the right number of chlorines on each side. We're going to use coefficients to do that. All right, so I'm going to kind of walk through what our coefficients look like and what that means for us in terms of the number of atoms in that molecule. Okay, if I look at 2H2O, that tells me I have 2 total water molecules. Okay, so I have 2 water molecules separate of each other, right? It's not a new compound that has 4 hydrogens and 2 oxygens. These are 2 separate water molecules. Okay, or we can scale it up to think about 2 moles of water molecules, which would be a lot bigger quantity. Okay, so when I look at this, it tells me I have 2 water molecules, which gives me a total of 4 hydrogen atoms, which would give me a total of how many oxygen atoms? 2. Good, 2 oxygen atoms. Do we see how that coefficient works? All you're doing is multiplying that coefficient through. Okay. And the reason we count the number of atoms is so we can balance both sides of those equations, right? We said we have to have the same number of oxygen on the left as we do on the right. So we count the total number of atoms to help us do that. All right, we talked about this last bullet here. Coefficients also represent the relative number of moles in a chemical equation. So you can scale it up to think about the number of moles, or you can scale it down to think about single molecules or single compounds. All right, we don't really need to look at that equation right now. Okay, so when we start balancing, you could be given the problem in word form, right? Potassium chlorate plus sodium nitrate, blah, blah, blah. If that's the case, the first thing that you want to do is write the chemical formula for all reactants and products and put them on the correct side of the equation. Okay, reactants are always going to go on the left. Products are always going to go on the right. What happens if I have more than one reactant? How do I show that? Do I multiply them? Do I add them? Do I subtract them? Any guesses? We add them. So if I have reactants A and B that form products C and D, I'm not just going to put like an and sign here. That's not how it works, right? We have to add them together. Okay? So you can have as many reactants as you want. You can have as many products as you want. That's fine. You're going to add all of those reactants, and that should equal all of the products. You can kind of think of this kind of as an equal sign, right? All of our reactants should add up to all of our products. Okay? Sorry. Do you want that picture up again? Okay, so once we have it set up in our word form, we're going to start the process of balancing. And the way we do that is we're going to balance each atom one at a time. Okay, and I don't even really need you to put this last part of it in here. Okay, I'm going to show you the process. It's going to make a lot more sense when we do the actual problem rather than writing out the steps. Okay, but it's important that you understand we have to balance these elements one at a time. Okay, so it's really each element one at a time. If you have polyatomics that appear on both sides of the equation, let's say nitrates on one side and nitrates on the other side, paired with a different cation, you can balance the polyatomic ions as a whole if you would like to. If you would still rather do each element one at a time, that's great. Do that too. Okay? It's completely up to you how you want to do that. Balancing each element one by one will always work. Right? But if you see polyatomic ions that are on both sides of the equation, you can balance those together. Typically, you're going to balance hydrogen and oxygen last. So if you have a chemical equation that has, 4 elements, you probably want to do hydrogen and oxygen last. They're usually the easiest to manipulate. Okay? Not always the rule, but that's a pretty good hint, I guess. Pretty good helpful clue. Okay, this last bullet here is important. Okay, it might take you more than one try to balance your equation. You might think you have everything balanced and then you're missing one hydrogen over here. So then you have to figure out something else, right? It might take you more than one try. So with that being said, I would probably maybe look at pencil for these, okay, because it's really hard to cross things out this many times. But the important part is once you balance it correctly, there's only one correct answer. You can check yourself. There should be no reason that you ever get a balancing equation question wrong because you can always check yourself, right? There's only one right possible answer. But it might take you a couple tries to get there, and that's okay. All right? Okay, are we ready to look at some problems here? I know this is still a little abstract. We want to see it happening, actually. Okay? Okay, so let's look at this chemical reaction right here. Can you see this reaction? H2 plus Cl2 yields HCl. Okay, do we think that equation is balanced? No, okay, this is a pretty good clue right here, It's on a scale that's not balanced. Okay, but how many hydrogens do we have on the left side? 2. And how many do we have on the right side?
1.
Only 1, right? How many chlorines do we have? 2. And on the right side we only have 1. So how do we fix that?
Do we just make it 2 HCl?
Yeah, can't we just add another HCl molecule? Yeah. Okay, so all I'm doing here is adding another HCl, and in my chemical reaction, I'm adding that coefficient. Okay, it's really important to understand we don't ever alter the chemical formula. We don't make it H2Cl2, right? That's not the same thing as 2HCl. Okay, we don't ever alter the chemical formula. We add a coefficient if we need to add atoms or add molecules or whatever we need to do. Okay, do not alter the chemical formula in any way. You add coefficients to help you balance that equation. Okay, questions here? Simple enough, right? So since there is no coefficient in front of this hydrogen gas or chlorine gas, what could we assume is there? There's no coefficient shown. What would it have to be? A 1, right? There's no coefficient there. We assume there's only one of those hydrogen gas molecules and one chlorine molecule. Okay? Okay, when we add a coefficient to our chemical formula, they never go in the middle, right? If we need to add a hydrogen, we don't ever see it go in the middle here. So let's see if I have water. I don't add a coefficient right in here because I need 2 oxygen atoms, right? That's not how it works. I add a coefficient to the front of the whole compound, which means I then double the hydrogen as well as the oxygen. Okay, so coefficients go in front of the whole chemical formula. Double check all of your chemical formulas, right? If you accidentally use sulfite instead of sulfate, that means you have 1 less oxygen, which could lead to not letting your equation balance. Okay? So if you are getting stuck and you're having a lot of trouble trying to get this thing balanced, you need to make sure that your actual chemical formulas are correct. that you used the correct polyatomic ion, you used whatever you needed to correctly. Okay. So double check your chemical formulas. Don't ever change subscripts. Okay. You don't get to alter a chemical formula. We've talked about that a couple times. I know some of this is repetitive. I'm sorry. Okay. Don't alter any chemical formulas. Just add coefficients. If you're able to reduce these coefficients, you can. So let's say I had a reaction A plus B is C plus D. Okay, these are some chemical formulas. And when I balanced it, my coefficients came out to be 2, 4, 2, 2. Okay, are all of those coefficients reducible by the same number? Yeah, so let's say I was balancing and I kind of just overshot it, right? That means I reduced this down to a 1, which I can leave off, 2, 1, and a 1. Okay, so you're able to reduce those coefficients if they're all reducible by the same number. Okay, and that happens sometimes. All right, let's try one. Whoa! I'm going to make you do it anyway. I'm going to show you kind of my method for balancing reactions, and it works well for me. If you find something better that works for you, that's great. What I'm going to do is I'm going to list all of my elements just kind of in a little line here. Copper, silver, nitrogen, and oxygen, right? Those are my 4 elements. This is my method for balancing. You don't have to use this way. This is just what works for me, okay? So the reason I drew a line on either side is to tell me on the left side this is how many I have, and on the right side this is how many I have. I want those numbers to match, right? If I can balance it, I want those numbers to match. So the first thing I do is go ahead and count them, okay? I'm sorry, I'll give you a second to finish getting that written down. Now I'm going to go through and I'm going to count how many of each element I have, just taking an initial count. So on the left side, how many coppers do I have? 1. How many silvers do I have on the left side? 1. How many nitrogens? 1. And how many oxygens? 3. Good. Any question about where those numbers came from? This was all left side of the equation, which is why I put them on the left side of that element. Okay. On the right side, how many coppers do I have? 1. How many silvers do I have? 1. Nitrogens? 2. I have 2 nitrogens because this 2 is distributed through there. So 2 nitrogens. And how many oxygens? 6. Okay, so do my numbers all match? No, they don't. Okay, so that means what should I start with? Nitrogen. Okay, I need a nitrogen on the left. I need another one. So what coefficient might I put here? 2. Okay. So does that changes the nitrogen to make it 2 nitrogens? It also changes oxygen, right? This 2 tells me I have 2 nitrogen atoms. How many oxygen atoms do I have now? 6. Okay, and I also have 2 silver, that's right. So now my copper matches, nitrogen matches, oxygen matches, but my silver doesn't. Yeah, so now I just put a 2 over here, which makes this a 2, which means all of them match. Okay, is that making sense? So then you go back and double check. Okay, I have 1 copper on either side. Good. I have 2 silvers. 1, 2, 1, 2. 2 nitrogens. 1, 2, 1, 2. And 6 oxygens. Okay. Not too bad, right? A lot of rules that go into that, but pretty simple.
Will they always give you, like, stuff on both sides of the...
Sometimes later on in the chapter, we're going to learn how to build our reaction based on just the reactants. But otherwise, yeah, if you're just balancing, they'll give you all of them. And you might only have 1 on one side and 2 on the other or whatever, but yeah. Questions here? Okay, if there's a 1, you don't need to include the 1. Okay, you can leave it out if there's a 1 subscript there. Okay, just leave that off. Okay, yeah. Let's try, we'll do the first 2 together, and then we'll try the last couple on our own. So go ahead and get these first 2 written down here. So for this first one, we have aluminum, bromine, and then it's going to form aluminum bromide. On the left side, how many aluminums do I have? 1. And how many bromines? 2. Okay, on the right side, how many aluminums do I have? 2. And bromines I have 6. Okay. So my first step would probably be to do what? I want to put the aluminum. I got to double the aluminum because I need this to be a 2. Right? I want these to match. Okay, so how many bromine molecules do I need? I need 3 of those. Okay, because 3 of each of those are going to give me 6 total bromine atoms, which means I match. So do I need to add a coefficient here? Okay, so there's a 1 there. I'm going to leave that off, but can I reduce this at all? No, right? It has to be reduced to a whole number. You can't have a fraction coefficient. If this was like, let's say this on this next one I had a 4 and a 2 and a 2, I could reduce those down so it's 2, 1, and 1. Right? We want the smallest, whatever, least common denominator or whatever. Yeah. I don't know the math term that goes with it. Okay, questions on that first one? All right, second one, pretty simple. Also, there's only 2 elements, so potassium and bromide. Okay, on the left side I have 1 potassium and 2 bromides. On the right side I have 1 of each. Okay, do we see where those are coming from? All right, so my balancing, right, I need 2 bromines. That means I'm going to have to add a 2 on this side. That alters bromine, but it also alters potassium. So now I've got uneven potassiums, which means I need to go 2 here. Okay, which matches both of those. Is this one reducible? No, right? Because this is a 1. So just because you see two coefficients there doesn't mean that's reducible. You can put the 1 if you'd like. More often than not, it should be left off. Okay? Things aren't going to be reducible that often. It only happens if you overshoot it, right? If you miss some connection and you doubled it when you didn't really need to or whatever, that would be when it's reducible. Okay? But if you do it kind of correctly from the beginning, you won't need to really reduce very many. Okay? Go ahead and try these next 2 on your own. I would do all the elements separately. So for the OH, you just have 1 oxygen and 1 hydrogen. Oh, sorry. No, you don't have to rewrite it. But you would just count like 1 oxygen on the right and then 3 hydrogens on the right. So for the total. What are you stuck on? See, that hydrogen, this hydrogen right here, is a single. On this side, would you ever have an odd number of hydrogens? No. So that means this has to be an even, right? We need this to be an even, so that combined with this 2, we get an even number of hydrogens. So we've got to think about that in terms of, we've got 3 on this side and 2 on this side. This one has to be an even number, right? So we can get an even number total.
So do you know work usually left to right or right to
I usually work, it doesn't really make a difference. No, yeah, whatever's easier. So here, right off the bat, on this sodium one, I know that I'm going to have to double this because I need to have an even number of hydrogens. So I'm going to start with a 2 there. And I'd say 2, and then that would give me 4 total hydrogens here, and 2. So then I got to go figure out something on the other side, right? I'd go 2 there, which gives me 4 and 2, and then I just drop 2 right there. Okay. Do we all agree with that sodium and water reaction? 2, 2, 2, 1. Okay. I talked about this a little bit here. what I want to point out with this equation, if you're not quite done with that, that's okay. With this reaction, could the hydrogens on the left-hand side ever be an odd number of hydrogens? No, because it's H2, right? So it could never be an odd number. However, on the right side, we have this single hydrogen hanging out in this molecule, which gives us an odd number on this side. That tells us that this compound has to be an even coefficient, right? Because we need an even number of hydrogens. So I would start right off the bat with doubling that one to give us an even number, and then that's going to show us where we can kind of go from there. Okay, so whenever you have a single element like that hanging out, you know it has to be an even number, start with that one. Okay? And then do we have the last one done yet or not quite? On the right-hand side, I have 1, 2 from this compound, and then 2 right here, so I have 4 total. Right? The coefficients just tell us... Wait, why were we supposed to have 5?
Well, there was 5.
On the left-hand side, before we started, there was only 2.
Yeah, and on the right-hand side before we started,
There was 3. 1, 2, 3. So it doesn't really matter how many atoms you start with before you balance the equation. We don't care about any of that, right? Once we get it balanced, then we look at the making sure everything is in line, ready to go.